Hello everyone. Welcome to this video documentary of a project on rainwater harvesting. This is a project undertaken by Group 1, that is roll number 55, Ishida, 56, Sumaya, and 67, Sahel of the N7 batch of TE7. Recently, rain precipitation has become increasingly irregular and inconsistent due to global warming and pollution. This has given a rise to unnatural droughts and flash floods, appearing in various parts of the world, which has started to severely affect the previously constructed water reservoirs for cities and villages. The purpose of this project is to provide a cost-effective and easily implementable solution to harvesting rainwater, and thereby reducing the stress on current water reservoirs. Theoretical background: Pune is the second largest city in Maharashtra, a highly urbanized state characterized by expanding cities that house approximately 42.5% of its population. Approximately 2.5 million in 2001 and projected to be 5.7 million by 2027. The city currently supplies over 650 million liters of water per day to its residents through a 2,000-kilometer-long pipeline. On the treatment side, approximately 68% of the city's sewage of over 300 million liters daily is treated by 5 sewage treatment plants. The existing resources are barely able to meet current demands. Multiple sources of supply need to be explored, tested, and implemented in the immediate future. With regional rainfall of sustainable volume and good quality, and growing demand on the urban water supply, rainwater harvesting is increasingly considered as a supplement to the main supply by resident households and as an urban demand reduction strategy by the Pune Municipal Corporation. The technical aspects of such supplementation are relatively uncomplicated. Rainwater harvesting is distinct from sources such as construction of new dams, water recycling or desalination that augment the reticulated supply, and is an attractive form of supplementing household supply for several reasons. In addition to reducing demand on main supply, household rainwater tanks can assure an alternative and independent household supply during mains water restrictions. Though somewhat dependent on end use and maintenance, usually of acceptable quality for domestic purposes, renewable at acceptable volumes through natural precipitation despite forecast climate change. Rainwater harvesting systems produce beneficial externalities such as reducing peak storm water runoff and associated processing costs. Simple to install and operate. Running costs are almost negligible. It is convenient and economical in the sense that it provides water at the point of consumption. System design. After going through all the available resources, the solution that was unanimously selected was an automated rainwater harvesting system powered by some sort of renewable energy. While the discussions progressed, the concepts of wind-powered system and solar-powered systems came up. Given that one of the important project parameters of wide availability in any situation plausible, solar power was chosen as a mean to power the system. Once the power source was decided, the next step was to select the sensor array to detect rain and subsequently give a positive trigger to the main microcontroller, which would subsequently send a signal to the DC motor connected to the flaps intended for rainwater harvesting. For rain detection, a generic rain sensor module was selected. Next in line was the microcontroller selection. The most fiscally conservative choice that did the required intelligent monitoring and automated processes was Arduino Uno Rev 3. The microcontroller was highly modular and sported a wider compatibility and most support to various sensor arrays. This easily made it the best choice for this project. Finally, the moving parts of this project, namely the DC motor and flaps, were kept largely as an open-ended concept to allow the automated system to interface with a wide selection of DC motors and flaps. Depending on the implementation, the DC motor driver circuit can be programmed to rotate the gears, opening the flaps for a set number of revolutions until the flaps are fully deployed and directing the flow of rainwater incident on the flaps surface into a funnel and subsequently into a tank as and when it rains. Next, I would like to invite the team to elaborate upon the circuit design and implementation.
Implementation. After the selection stage for the component was done, the primary setup was setting the microcontroller at the center of the board with the rain sensor to the input left side and the DC motor driver and motor to the output right side, and power the entire circuit with a solar panel charging a battery and subsequently powering the microcontroller and DC motor. At the input side, we have the rain sensor module. The working of rain sensor is pretty straightforward. The sensing pad with a series of exposed copper traces together act as a variable resistor, just like a potentiometer whose resistance varies according to the amount of water on its surface. This resistance is inversely proportional to the amount of water. The more water on the surface means better conductivity and will result in lower resistance. The less water on the surface means poor conductivity and will result in higher resistance. The sensor also has an electronic module that connects the sensing pad to the Arduino. The module produces an output voltage according to the resistance of the sensing pad and is fed to an LM393 high precision comparator to digitize it and make it available at the digital output pin. The module has an inbuilt potentiometer for sensitivity adjustment of the digital output, so that when the amount of water exceeds a threshold value, the module will output low, otherwise high.
Processing. The entire automation is shouldered by the Arduino Uno microcontroller. It takes the digital input from the rain sensor, which, after being internally processed from analog to digital, reads as 1 when it rains and as 0 when it stops raining. Upon detection of rain, the sensor sends a trigger to the microcontroller, which then runs the internal code to send a signal to the DC motor to rotate clockwise for a set number of turns. If and when it stops raining, the sensor sends a 0 to the Arduino, which then sends a signal to the DC motor to rotate in anti-clockwise direction for the same number of turns.
At the output side, a DC driver circuit controls the rotation of a DC motor, connected to the gears controlling the opening of flaps. This end of the circuit is largely open to a multitude of settings, based off some small changes in code, thereby allowing a wide array of flaps of various sizes to be deployed as and where necessary. The DC driver simply directs the flaps to open or close when instructed by the microcontroller automatically. In case of a power failure or circuit failure, the flaps provide a rod which rotates the gear assembly, allowing for the manual deployment of flaps.
Thank you, Sumaya, Ishita, and Sahil for explaining the implementation of the circuitry for the project. Rainwater harvesting is becoming an increasingly important discussion moving forward into the next stage of technological development, in the face of problems such as global warming and limited resources that the planet has. This project provides a cost-effective and modular method to combat wastage of resources and developing increasingly efficient environments. The successful implementation of automated rainwater harvesting in a simulated environment, namely the Proteus design suite, paved way for the team to brainstorm further ways in which the modularity of this project can lead to the successful implementation of this framework to various systems hosted in a large selection of environment based on the type of flaps and DC motors used in its base design. Through the various sources and references, this project provided valuable insight in the field of sensor-based automation, hence, providing the team a significantly deeper understanding in the design and implementation of various sensors and security systems and the challenges faced in each of the applications. This further enriched our knowledge on how intelligent systems can be designed to make day-to-day life easier. Thank you all for tuning into the video documentary, and a special token of gratitude to Professor D.M. Shinde for guiding the team through the project.